Hi physics students, this is Mr. Scott and this is your Newton's Laws review screencast, and today we're going to be looking at our good friend Nellie Newton as well as some of the chunking slides from the chapter. You may remember Nellie Newton as the girl who held up the apple for at least 20 minutes while we reviewed the backside of workbook 6-1. Okay, let's get started. So usually your workbook uses an N and a W to represent the normal force and the weight. We typically like to write F as a force and then put the subscript of whatever it is down below. But don't get tripped up by this. It's just the same two forces you're used to. Okay, so in this situation we have two forces acting on the apple. And usually we would, start a free body diagram, box up the apple, and show both these forces from where they're acting on the apple, and then calculate a net force. Well, in this case, if both forces are equal, we could expect that this net force, when you add up the normal force and the force of gravity that go opposite to each other, have to be equal to 0 newtons, right? Well, if either one gets bigger, that means that our net force will no longer be 0 newtons, but it will be an unbalanced force acting on the apple. And thereby by Newton's first law and second law, we have to have some acceleration of the apple, either down or up. So if the normal force gets larger because Nellie starts to push on this apple with more force than she had previously, we'd start to get a larger vector going up, a smaller vector going down, and therefore our net force would be something going up and accelerating the apple upward. But if Nellie decides to move her hand out of the way, then the apple would just fall. We'd lose all the normal force altogether, and this would just become an object in free fall. Okay, so in this situation with Nellie holding up an apple, one of the most missed questions every single year is, are the normal force and the weight an action-reaction pair? Think about that for a second, and if you said no, you win. The reason why is because they act on the same mass. An action-reaction pair, by definition, has to act on different masses. And in this case, when you draw a free body diagram, yes, you have a normal force that is going upward and a weight that is going downward, and they are equal if we're at equilibrium here. But, like we said, acting on the same mass, they are not an action-reaction pair. The action-reaction pairs are not being shown here. The normal force is the hand pushing up on the apple. So the action-reaction pair to that must be the apple pushing back down on the hand, which would be in the hand's free body diagram, but not the apple's. And then the weight would be the earth pulling down on the apple, and the apple pulling back up on the earth. Even though they're not touching, that's an action-reaction pair, and because these two forces that are acting on the apple are included in a free body diagram, it shouldn't confuse you that they're an action-reaction pair, because there are other forces involved acting on other objects. Another problem that physics students typically have in this chapter is knowing how to calculate mass from weight or how to figure out weight from mass. So I have, said it till I'm blue in the face to my students, but we have to know that F equals ma can be changed into Fg equals mg. And this is such a simple equation, it's an easy, calculation to do, but just so many kids will sit there, look at the word mass, and then not know how to figure out how to get it from a weight of, let's say, 50 newtons in this case. So once you know that the gravity is always going to be the same here on the surface of the earth, you can divide that to the other side and solve for the mass in question. So 50 newtons divided by, let's go with 10 meters per second squared, and round up just a bit, and you end up with a mass of 5 kilograms. Now we could also go the other way, and if you know the mass, you can figure out the weight by just multiplying by 10 meters per second squared, which is the surface gravity here on Earth. But you have to know the relationship between weight and force of gravity, and that they're the same. And you have to know that if you know the mass, you can figure out the weight, and if you know the weight, you can figure out the mass. If not, you'll probably not like your score on this test, but also the final coming up in January. Alright, so let's say that Nellie is holding this apple outside, and now all of a sudden a gust of wind comes and pushes the apple sideways, and our free body diagram to the apple now changes. We add the third vector, which is now the force of the air pushing on the apple sideways, and if we know the magnitude of all three of these vectors, we can put them to scale and have this be a perfectly scale vector diagram. So let's add some made-up values here for the weight, the normal force, and the force of air resistance. Did I mention this is a really heavy apple? Now from our notes we know that there are 4 steps to solving any Newton's second law problem, and we've just done one by drawing the free body diagram fully. The second part is now figuring out the force components in both directions, horizontal and vertical. Because we only have one force acting horizontally, that means that this is easy. The net force horizontally must be equal to the force of air resistance, or just 60 newtons in this case. Now vertically you have 2 forces, but again, because one is 50 newtons of weight, and we can assume that this apple is at equilibrium at the time that the air pushes on it, we would have 50 newtons of normal force too. So because of that, they must cancel out, and we end up with 0 newtons of net force vertically, and our only acceleration is horizontal. So now we're 2 out of 4 steps down, and the next step is to figure out the net force. In this case, we have a net force of 60 newtons to the right and a net force of 0 newtons vertically. So that means it's a little bit easier than normal. Our net force is just going to be equal to Fx plus Fy, and because one of them is 0, we just get left with the other as the net force. So we would end up with 60 newtons plus 0 newtons being equal to 60 newtons to the right. Okay, well, most cases, though, that we will give you will be a little bit more challenging. We might have 2 forces that are unbalanced in 2 different directions. If that's the case, all you have to do to change this calculation is create a right triangle diagram, tip to tail, and let's say that Nellie gave a little bit extra push upward and gave it more normal force than we had a force of gravity at the time. We would then have 2 vectors, one going to the right and one going up, that we'd then add up in the Pythagorean theorem to calculate the net force. And then we'd say, okay, the net force squared equals the force of air squared plus the normal force squared, and then take the square roots of both sides to solve for net force. The last step in a problem like this would be to try and solve for either the mass or the acceleration. Now on the previous page we already solved for the mass and found that it was 5 kilograms. So let's say that we ask you a question like, okay, what's the acceleration on the apple at that second? So in order to solve for this, you're going to go back to Newton's second law now that we know the net force and say F net is equal to ma, and we want to solve for a, so we got to divide m to both sides and now plug in and solve. So lastly, we get the acceleration to be 12 meters per second squared at that moment on the apple. Alright, for the last part of the screencast, let's go through the chunking slides for the chapter, which are available on the website. Your teacher may not have gotten to this in class, or maybe you're absent, or maybe you just want to hear it a second time. It usually highlights some of the more important topics, as well as some of the pitfalls that kids have when they go into the Newton's law test. So the first law is the law of inertia, and when we do the first law, we always are wondering, is there an unbalanced force? Okay, that means is there a force that will be going horizontal or vertical that is not canceled out with another force in the free body diagram? And if there is, we must accelerate and change our velocity. So forces cause a change in velocity. So a lot of times kids don't understand what the word inertia means. And inertia is just a property of matter to resist change of an unbalanced force. So if you have more mass, then you must have more inertia, and you must want to resist the change of an unbalanced force more. So they're directly related, and even though you can't measure inertia with any units, you know that if you have twice the mass, you must have twice the inertia. If you have half the mass, you must have half of the inertia. Okay, so Newton's second law is probably the most important law of all physics, because everything that moves must be moving for a reason, and it's usually because of a force, and we can calculate that force by using equals ma. And F can be many different forces. It could be one force, it could be a million forces, but if you know the net force after adding up all the other forces acting on a mass, then you can figure out its acceleration and use all the equations we've used in previous chapters. Now we already said this in previous slides, but don't forget that this is 9.8 meters per second squared for little g, which we might round up to 10, and as long as you know the mass, you can figure out the force of gravity. And also realize that this is only for Earth, so if you go to some other location in the solar system or the universe, that surface gravity, or that little g, might be a different value. Also in this chapter, we talked a lot about when we're at equilibrium, or a net force is 0. So there's two ways that you can be at equilibrium that we've covered. The first one is to not be moving, or to be still. And the second one is the one that kids have a lot of trouble with, and that is to be at a constant velocity. If an object has a constant velocity, back to Newton's first law, it would just be an object in motion staying in motion. There's no acceleration, because acceleration is equal to the change in velocity divided by the change in time. And because of F equals ma, that means that you must have a net force of 0 if you have an A of 0, just because you can't multiply anything by 0 to get a different value than 0. Be sure not to forget about how we did equilibrium cases where we had things hanging with forces of tension, or we had a normal force that was pushing up from a surface, or times when we had air resistance and terminal velocity, all of which would be examples of net forces of 0. And the last part of Newton's second law that we should probably remember is that acceleration and net force will always point the same way, but they don't have to point the same way as velocity. So you could be slowing down and have your acceleration and net force point the opposite way of your velocity, or you could be speeding up and have them all point in the same direction. For the third law, we always know that forces come in pairs and that action-reaction pairs must be equal and opposite and act on different masses. Because of this, they don't cancel out unless they are in internal forces to a combined mass or a system. We also gave you many clicker questions and practice problems on workbook page asking about impact forces of two different objects that collide with different masses. And remember that we can go back to the second law, and as long as we have an action-reaction pair being equal to each other, we can say that their product of mass times acceleration have to be equal too. And because of this, if one has a bigger mass than the other, the acceleration has to do the exact opposite to compensate for that multiplication and make sure that both sides of the equation are still equal. So we gave you the example of a bug in a windshield. Because the bug is so much smaller in mass, it's going to have a rapid acceleration and even change its direction and go backward. But even the car is having a small acceleration from the bug's mass hitting it, but the forces acting on both must be equal. And lastly, we did free body diagrams over and over in this chapter, and remember that when we do a free body diagram, it is only for one mass. So figure out what is pushing, pulling, tugging on that mass, and then label it correctly with the right force every time. And then, if you need to do calculations, follow your 4-step process. And my last bit of advice for this chapter that I would recommend to you guys is to make sure that you label the forces correctly. So many kids get confused about the difference between force of tension and normal force, or the force of gravity and mass, or just knowing definitions of the words is so important, and it shows understanding. So here's a list of all the different forces that we've covered in this chapter, and there's been more, but you can always make up a name for the other forces. These are the ones that continuously come back up. And as long as you don't mislabel a force, we'll probably give you credit for it. So note, the force of friction and the force of air resistance really are kind of saying the same thing, just a different way of saying it, because air resistance is the force of friction, and force applied could be many different things. But like I said, as long as you have them labeled correctly for the ones that we always tend to use, which are the force of gravity, and then make sure you don't confuse tension with normal or something like that, you should get all the points on your test. Well, that's it for me, kids, and hopefully you do well on your test. If you are still worried and you need more help, feel free to come in for help before or after school. Look at your workbook pages, your reading guides, your web assigns, and any other resources we've given you through the chapter. Good luck, guys, and I'll see you on the other side.